Hi, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. I was thinking I've been doing these for, a couple of years now, since the beginning of the pandemic. I don't know, that's after pandemic time or something of 2 years. Anyway, I'm happy to answer specific questions, but I'm also happy to just try and riff and talk about topics in science and technology that I might know about. And I see we have a few questions left over from previous times. Okay. Let's see. There's a question here about agriculture and asking about cellular automata and agriculture. Well, let's see what I can do with that. One of the things that, first thing to say about agriculture is it's been pretty successful all in all. There were at different times in history, people were saying, oh, if there are lots more people, we won't be able to grow enough food to feed them all. And it's turned out that that hasn't been the case. And the reason has been that people have realized that it's possible to make more efficient crops by breeding crops and so on. That it isn't the case that the things that were the kind of naturally occurring kind of crops from long, long ago are what we have today. I always find it interesting that everything we have, whether it's potatoes, apples, or any of these kinds of things, they all originated in some particular place in the world. I think potatoes in Peru, I think apples maybe in Kazakhstan, places like that. And it's kind of interesting that these things that have turned out to be really a good fit for us humans as, oh, we really want to eat this stuff, they've arisen in different sort of tiny niches in kind of the biological ecosystem of the world. It's also interesting that sometimes, I think it's true with apples, for instance, that the way that one gets kind of the apple tree that's going to make good apples is not by letting the thing naturally reproduce, but rather by taking a cutting from one tree, basically, and saying, let's have a thing that is essentially a clone of that previous tree, and we'll keep cloning that tree to get the apples that taste the way we want them to taste. I think that even a small change in the genetics of the apple tree leads to a pretty large change in, for example, the taste of the apples, which is why, there are particular named types of apples which really are genetically identical and have been for a long time. And people talk about, heirloom different kinds of fruits and vegetables and so on. And that has to do in part with this question of whether, where is the genetics coming from for these things that we're eating and so on. I think it's a thing where, when one asks the question, how do you optimize things like crop yields and so on? I'm not sure that one sees all kinds of technology that people try to develop to do that. And I've seen over the course of time quite a number of kind of hoped for AI type applications. I think in current times, drones have been a pretty big sort of capability addition for, you send out the drone, you have it go and study the, check out your field and things like that. A thing worth realizing is that, to know what's happening with a crop, you can look at it with your eyes with sort of ordinary visible light. But if you look at it, I think particularly in the infrared, if you look at the heat signature of it and other things, you can tell a lot more about whether the plants are growing and things like that. And so, for example, every day there's satellite imagery that's produced of the Earth that shows all these different places where crops are being grown, and you can kind of deduce from those satellite images, particularly outside of the visible range, you can deduce all kinds of things about how well the crops are growing. People who are interested in kind of trading financially on sort of the success or not of some crop yield are always studying those kinds of things to try to make predictions about, will this be a good season for such and such a kind of crop in such and such a place and so on. In terms of a different question, which is when you have a bunch of plants growing and you're trying to ask questions like, what will be the sort of competition between these plants locally and so on. So for example, let's say you have a forest and you have two different kinds of trees. And it can be the case that you have sort of rules of interaction between these trees. Like if one tree is growing, it might suck all the nutrients out of that area of the soil. Or if one tree is growing, it might shade all the light for nearby trees and so on. And so there's a question of how can you make kind of a model, typically a computational model of a system like that, where you, let's say, have two types of trees and you're asking how do you get competition between these two types of trees and what kinds of patterns can you get? And one of the things that's kind of fun is that there are situations in which you will get kind of these sort of variegated striping patterns and things like this that you can see from satellite imagery, and they look bizarrely similar to the patterns that you see on zebra stripes and things like this. And the reason they look bizarrely similar is because actually the mechanisms are very much the same. They are sort of mechanisms of things spreading out, diffusing out, things sort of reacting with each other and inhibiting other things from growing. So it's sort of a general process that happens in lots of kinds of systems, that when you have growth in one place, you inhibit growth nearby, and that produces certain characteristic patterns of behavior. But it's kind of striking to see that sort of the pattern of growth of different kinds of trees in a forest can look very similar to the pattern of pigmentation on a zebra or something like this. And it's this whole idea of kind of things growing and sort of inhibitions to growth when things grow, kind of the most classic version of this is snowflakes. When you have a crystal, an ice crystal that's growing, kind of in many cases, what happens in the ice crystal is the water molecules line themselves up and it makes kind of a hexagonal. The water molecules form this at a microscopic level, form this kind of hexagonal array. And the most obvious thing to have happen would be that you get kind of a hexagonal shaped crystal progressively growing, laying down layers of water molecules on the growing edge of the ice to make a hexagonal crystal. But in fact, snowflakes don't just make usually simple hexagonal plates. Sometimes they do make simple hexagonal plates, but often they make, if you look at a snowflake, it has all these kind of tree-like arms, dendritic snowflakes. And that's what makes snow fluffy, for example, and is that all these snowflakes aren't just flat plates that would, if when in situations where you do have just flat plates of snow crystals, things will tend to be quite slippery, and that's a big deal if you're trying to predict avalanches and things like that, whether the snow is slippery or whether it's fluffy. And what makes it fluffy? What makes it fluffy is that when a piece of water, so a snowflake forms by starting off from some tiny seed. Maybe it'll be a piece of dust, maybe it's something else, some tiny little seed that then starts accumulating ice. And it can accumulate the ice if it's in a cloud, for example, there can be an updraft of air that's keeping the snowflake sitting in this place where there's a whole bunch of water vapor. The cloud is sort of made of water vapor, and it's keeping the snowflake there, and the snowflake is gradually growing. And the question is, how does it grow? And fundamentally what's happening is that you've got this crystal and it's having water molecules kind of accrete to the surface of the crystal. And as they hit the crystal, so to speak, they freeze, they become solid, they attach to the crystal. The question is, how does that happen? And the question would be, do they do it in a very orderly way where they're just laying down one layer on top of the next layer and so on to make this sort of hexagonal plate? Or do they do it in a different way? And what tends to happen is when a little piece of water, bunch of water molecules have attached themselves to this solid snowflake, they release heat when they do that. Essentially what's happening is the water molecules are floating around and then they get dragged in. They get, by the forces that hold the crystal together, they get dragged in by those forces. They lock into the crystal And as they lock into the crystal, the energy that they had that was making them kind of bounce around in water vapor, that energy has to be is released as heat. Because the thing, it's that energy of motion has been taken away by the fact that the water molecule has been locked in place in the crystal, and so it's released as just heating up the crystal. So what tends to happen is when a piece of water, molecules of water, attach to the glowing surface of the crystal, they release a certain amount of heat just at that place where they're attached. And so what that means is that the chance of the next water molecule attaching there is going to be lower, because the water molecule will only attach when the temperature is low enough that there's freezing of water. And so there's sort of a local place where things warm up, and it makes it less likely that the water molecule will attach. So that leads to kind of a phenomenon of growth inhibition. Once you've attached water, once you've attached a piece of the ice crystal in one place, kind of heats it up locally and prevents it attaching nearby. So what is that going to do? Well, what that does is you start in a particular place, the thing will grow a little sort of knob out where some water molecules attached, but there won't be water molecules right next to that little knob, and instead there'll tend to be more water molecules added sort of to the end of the knob, and it keeps on going, and it's kind of going out in a sort of a line from the crystal, and then there's enough of kind of an area on the side that you can make another line coming out. And pretty soon you make a thing that kind of looks a bit like a tree, because it keeps on branching. And that's kind of how the snowflake is formed. And what tends to happen, I was very surprised when I discovered this, actually. I had a model for snowflake growth a long time ago that's just based on a simple kind of program in which one just thinks of sort of regions of ice crystal that are little hexagons, and you start asking, how do you, in this array of hexagons, how do you add a new hexagon to correspond to the freezing of more water? And it was a very simple model where, for example, you just say that at every step, you have a series of steps. At every step, you just say, add something if there's only one sort of frozen hexagon next to you. So if there are no frozen hexagons next to you, then you're away from the growing crystal, and nothing happens. If there are more than one hexagon next to you, then don't grow there at the next step. Only grow where there's exactly one hexagon there. And what that causes to happen is you grow these arms, and then the arms grow arms, and then the whole thing kind of trees out. One thing that model implies is that after it's treed out for a while, all those arms will end up colliding with each other. And so you'll go from a snowflake that was originally like this one hexagon in the middle, let's say, it grows a bunch of arms, then the arms crash into each other. It turns out that eventually, when the arms have kind of coalesced, you'll form another much bigger hexagon, although that hexagon will have little holes in it from where kind of the arms didn't quite match up as they collided with each other. And so many years ago, I was like, okay, I wonder if this actually happens in snowflakes. And yes, indeed it does. So that's an encouraging thing for that kind of very simple model that's based on just this phenomenon of growth inhibition. Now, it's, there are these things like people say, no two snowflakes are alike. I don't think this is true. What happens is that as a snowflake grows, it goes through many different kinds of shapes, from a plain hexagon to little arms, to arms with arms on them, to very many arms to arms to arms. And then it goes back to being a hexagonal shape. It has a wide diversity of shapes. So as the snowflake grows, it goes through this whole series of different possible shapes. And depending on which shape it gets to depends on exactly how long it was growing for. And to some extent on the conditions that it encountered when it was growing. What was the temperature, what was the humidity, how much water vapor was there in the air, and so on. And when you get two snowflakes, you catch them on your hand, or you catch them on a piece of fabric where they don't immediately melt, you'll see these two snowflakes might be quite different. But what happened is that any given snowflake will just go through this series of stages. And depending on at what stage it fell out of the cloud and you caught it, you'll see very different shapes. But then two snowflakes that landed nearby, the issue is that those two snowflakes may have had very different histories. And the reason for that is that there are currents in the air, and the snowflakes are falling through the air. It's not the case that the snowflakes all fall straight down like rain or something. They instead fall, they kind of float in the air, and they wiggle around and so on. And so it tends to be things like turbulence in the air, the fact that there are sort of these random patterns of flow in the air that cause snowflakes, even when they started nearby in the cloud and had kind of the same growth process, those two snowflakes, as a result of the kind of randomness of the turbulence of the fluid flow in the air, will tend to get separated. And so the snowflakes that arrive on your hand or whatever will tend to have been snowflakes that came from very different places, because snowflakes that were nearby will have been separated, and the ones that end up nearby will have come from very different origins. So that's kind of why you end up with this idea that no two snowflakes are alike, is because there's sort of this diversity of shapes, and then the actual sort of histories are very much mixed up by the process of the snowflake falling through the air. Now, I think so it was a little bit on. I'm kind of led to talk about we're talking about agriculture. I'm led to talk about a few aspects of that. I mean, one sort of interesting is that a lot of modern statistics, which one still calls modern statistics, although it's not so modern anymore, was invented by people who were trying to do agriculture research, particularly in the 1930s. And I remember actually when I was growing up in England, there was a famous agricultural research station that was near where I lived. And what had been done there is people they got fields, they had these sort of test fields, and they would break the fields up into different squares, and they would plant different crops, or they would use different fertilizers on those different squares. And then the question was, what could you tell about what would happen, what the yield of the crop was, how tall the thing would grow, what these different features based on these different things that you would do, add fertilizer, put this or that thing on the ground, do this or that, try out different kinds of things. And that, the origin of kind of, so the thing is that when you do those kinds of experiments, it isn't the case that it's a precise thing, like a sort of mathematical thing where you just say, add this and this and this, 2 + 3 + 4 equals some definite number. It's you heat the ground up, you put this fertilizer on it, you do this, you do that. And, some of the corn plants will grow this high and some will grow that high, and this one will do this, and so on. There's a whole range of possible results. And so the question then is, for example, let's say you've had 2 plots, and one of them you put fertilizer A on, one you put fertilizer B on, and you're looking at which one makes the corn plants grow higher. Well, you'll see that some corn plants grew higher in the A patch, and some grew higher in the B patch, and there's a whole distribution of heights in the A patch and the B patch. And so there are questions like, if you had some number of corn plants, let's say you had 20 corn plants in each patch, and you saw this or that result in the A patch versus the B patch, is that significant or not? Or is it just chance? So you can get some idea of that by looking at, for example, how broad is the distribution of corn plant heights in patch A? And what will typically happen is, so for example, something like that, heights. I don't know specifically for corn, I do know for humans that the distribution of heights in humans is so-called Gaussian or normal distribution. So if you take lots of humans and you say, how tall are these humans? And you just say, how many humans are 5'9" tall? How many humans are 5'10" tall? How many humans are each of those 1-inch bins? And you make a plot, a histogram, where you say how many humans are of each of those heights. What you'll find is that the number of humans of a particular height, you plot that, will form this kind of bell curve distribution where, I don't know what it is in the modern US, what is it, maybe, I think 5'8", 5'9" is kind of the center of that distribution for men at least. And so there's this kind of curve, and the peak might be around, let's say 5'9", and then it will have a certain distribution. So there'll be some people who are 4 feet 10 inches tall when they're adults. There'll be some people who are 6 feet 5 inches tall. Those have lower probabilities. They'll be lower down on this bell curve. So it is pretty typical to find lots of kinds of things which are distributed according to this kind of bell curve Gaussian distribution. And human height is one of them. Human weight is not distributed that way. Human weight follows a log normal distribution roughly, which is a somewhat different distribution. One thing one can ask is, why is it common for things to follow this Gaussian or normal distribution? It turns out there's actually a pretty good reason for that, which is, let's say you have a bunch of things you're working out. You're picking numbers at random, and you pick 5 numbers at random, and then you take the average of those 5 numbers, and you say, what's the distribution of the average of those 5 numbers? Turns out, if those numbers are sort of just numbers within a certain range, let's say 0 to 1 or something like that, and you take the average of, let's say, 5 numbers or something, you'll find that the distribution of the average is very close to a Gaussian distribution. That's a general result. It doesn't matter what the distribution of the individual numbers is. When you add them together and take their average, the distribution of the average is always close to this Gaussian distribution. And even 5 numbers is enough to get pretty close to a Gaussian distribution typically. It's the same kind of thing and that phenomenon, it's a mathematical result called the central limit theorem that says that if you have a bunch of numbers and they're all distributed in such a way that, for example, they're distributed in a limited range, they can't be, one of them can't be infinity, it's got to be, let's say, between 0 and 1, so long as it's in a fixed range, then if you take enough numbers and you average them together, the distribution of the averages will always be the Gaussian distribution. And that's why, because quite a lot of things are sort of the aggregate of many effects, that's why it's quite common to find Gaussian distributions as the distribution of things. The log normal distribution that I mentioned actually is also something that comes up quite often, because whereas the ordinary Gaussian distribution or normal distribution comes up by taking the average of numbers when you add them together, if you have a bunch of numbers and you multiply them together, and then you take the geometric mean, so you're taking if you'd have n numbers, you take the nth root of the product of those numbers, then the distribution of those things follows this log normal distribution. So when sort of things multiplied together, you'll tend to get this log normal distribution. When things added together, you'll tend to get a normal distribution. Now, so given that you have this normal distribution, it has a certain mean, that's sort of the average in the middle, and it has a certain standard deviation. That's essentially the width of the distribution. That's how, and the one standard deviation is, if you go from the mean, you go out one standard deviation, then one of the important results is that 68% of the the mass of the distribution is inside the band from mean minus 1 standard deviation to mean plus 1 standard deviation. So what that means is that if you say, oh, I'm within 1 sigma, 1 standard deviation of the mean, you're saying that you are no further out than that 68% of the population is within that range, that 1 sigma range, from 1 standard deviation below the mean to 1 standard deviation above the mean. And so when people say, oh, that's a 3 sigma effect, what they mean is that the effect is something that the chance of that happening is that is 3 standard deviations away from the mean. And the chance of that happening, you can kind of read off from the Gaussian distribution. What is it? It must be down in the 0.2% or something like that. I'm not sure. For 3 sigma, I should know, but I don't. The formula is, it's e to the minus x squared is the form of this distribution, and I certainly can't do that in my head to work out what the 3 sigma. Let's see, it's e to the minus that would be, so 1 standard deviation would be e to the minus 1, basically 1 over that's the height of the distribution. 1 over e is 2.718, so that's about the curve would be down at 1/3. Now, what you actually need to know the total amount within within one standard deviation is you need to know the integral, which is a thing called the error function ERF, and that goes far beyond my ability to work these things out in my head. But in any case, the point is that you'll have this distribution. So we're talking about crops, for example, and you say in patch A, there's a Gaussian distribution of heights, and its mean is this, and its standard deviation is that. And that's what we measure based on the particular, we can measure the mean and standard deviation. We can guess that mean and standard deviation is distributed according to a normal distribution. And given what we measured, we can deduce something about what we think, if it was that distribution, what distribution would it be? And then in patch B, we would have same kind of thing, let's say. And then we're asking questions like, is patch A far enough away from patch B in terms of the means that we measured to say, yes, patch A is more successful than patch B, for example. And you can ask things like, what's the distribution of the differences between means, between two Gaussian distributions? And that's a thing called the student T distribution, for example, is that, or the ratio of the variances, which is the square of the standard deviation. And that's another thing, I think it's called the F ratio distribution. So each of these things is something that sort of mathematically can get worked out. And then the question is, given that you might want to know, is fertilizer on patch A better than the one on patch B? You make these measurements, you need to ask, is there a significant effect? Is it significant based on the fact that our 20 corn plants, 12 of them were taller than the ones in the other patch? Is that a significant effect? And for that, you have to have some kind of theory of what's going on. You have to have some model that says if you had an infinite number of corn plants, they would follow this Gaussian distribution, and we're sampling from that, and we have this consequence, and so on. And it's kind of there's a whole sort of development of how one thinks about that came from the 1930s, that in today's world is very much used in medical testing, for example, as a way to say, is this effect significant? If X number of people take this drug and some percentage of them get better, is that a significant effect, or is that kind of what we would expect by pure chance based on looking at what happens in a population which didn't take the drug, and so on? Anyway, a few riffs on talking about that. Let's see. Some very technical questions here. Let's see. There's a detailed question from Wadanaz about a book called Structure and Interpretation of Computer Programs, which I think is by Hal Abelson and Jerry Sussman, maybe, both people I know, although I haven't seen the second of those people in quite a while, decades. But it's a book that's somewhere on my shelf along with 8,000 other books. The real, I would say, sort of a question about computing and programming and how to think about it and how to learn about it and so on. And this is something I've certainly thought quite a bit about. There's sort of, computers are built in a certain way. They have their intrinsic operations, instructions, and so on are set up and have been set up pretty much the same way for the whole history of computing, which is now about 2/3 of a century. The question is, when you as a human want to tell your computer what to do, how do you best explain to your computer what you want it to do? How do you best, in particular, set up a program that your computer can run that will make it do the things that you want it to do? And the kind of traditional approach of programming languages has been the computer has this intrinsic way of working. Let's try and make that be something where a human can slightly more conveniently tell the computer how to do things in the terms that the computer knows how to do. I have to say that the thing I've been trying to do for the last 40 years or so is to build what we might call a computational language, different from a programming language, a computational language where we start from the things that we want to think about and the ways we think about things, and we find a way to use kind of the concepts of computation to kind of crystallize the things that we think about. And then it's the job of the implementer of the language, of the computational language, to turn that sort of crystallized version of our thinking into something that can actually be run on the computer. And one of the things that's very helpful about sort of the computational way of presenting ideas is that it kind of it provides a structure that lets one kind of structure one's thoughts in an organized way. It's very much the same kind of phenomenon as happened with mathematics and mathematical notation. Mathematical notation as it is today is about 400 years old. Things like plus signs and equal signs and things like that. Before that notation existed, people had a pretty hard time expressing things mathematically. They had to use just words to say you add this to that, and then you multiply it by this, and then you divide it by that, and so on. And it's you know, if you try and write sentences that explain mathematics, they get very clunky very quickly. With mathematical notation, one has kind of a streamlined, succinct way to describe sort of describe a mathematical thought, so to speak. And the thing I've been trying to do for the last 40 years or so is to build a kind of computational language that allows one to describe things one's interested in talking about in computational terms, whether those things are things about a collection of objects, a collection of numbers, whether they're things like a collection of cities, whether they're things about, I don't know, distances between cities, whether they're things about images, and asking about kind of, you know, what are the things in this image and so on, the things that one might actually talk about in kind of discussing the world. We want to present these in a way that is kind of represented computationally, and where one can then have one's computer help one to figure out what to get answers and so on. So the kind of the traditional the kind of the programming language approach is computers are the way they are. Let's try and put a layer on top of that that kind of tries to let humans access it, to try and say, well, a computer has something where when you execute instructions on a computer, you have a program counter, and you are successively executing this instruction, then this instruction, then this instruction, and maybe you make a loop and you say, now after you get to this place in the program, go back and redo this computation and keep computing again. And so, for example, let's say you're trying to make a list of numbers, a list of the squares, you know, the numbers n squared from n equals 1 to 10 or something. So one way you can do that is to say, let's do it the way a computer would do it inside, which is to say, we'll have this number n, and n would first be equal to 1. We set it equal to 1. We store 1 in the memory location of the computer that corresponds to n. Then we evaluate n squared. Then we go back and we run we tell the computer, no, change what's in the memory location for n, add 1 to it, make it 2. Okay, compute n squared. Now go back, go back to the piece of program that said change the value of n, and now do the next thing. And so that turns into, like in a language like, I don't know, the C programming language, that would turn into a loop that says, you know, for n equals 1, n less than 10, n plus plus in C, that's n equals n plus 1. Then you say, well, what do you do with that value of n? Well, you'd have to have started building up a list of numbers. So you'd have to start up, before you even start that for loop, you have to say something like, you know, array has nothing in it. And then you have to, as you get to the nth number, you have to say, as n gets to be 7 or something, you have to say, okay, put the 7th element into that array, append this thing to that array. Then when you finish doing the loop, you say, okay, now give me the collection numbers you just generated. Okay, that's something where you're kind of describing what to do at the level of the raw computer. It's got a program counter, it's got the values of variables stored in memory. You're allocating memory to say how you want to add things to that list of numbers, things like that. Well, that's not the way humans think about it. The way humans would think about it is, okay, I just want to make a table of n squared, n goes from 1 to 10. So why not just say that to your computer? You know, table n squared, n 1 to 10. Well, turns out you can. And that's kind of the idea of computational language, is just say things the way we as humans think about them. Don't pander to the details of the engineering of how computers happen to be made. And so that's a thing which it's kind of funny, because people have a habit of kind of trying to teach people about computation by saying, let's think about how computers work inside. It would be like saying, you know, imagine you're trying to learn to drive a car. Let's start off on, you know, day one, let's learn how fuel injection works in an engine. This is, it's kind of a strange feature of kind of the way that computing evolved, because in the early days of computing, you know, you go back 50, 60 years ago, computers were really expensive things. And it was very important. The humans were cheap. You know, any kind of, oh, we're going to spend more effort to program this computer. It's like humans cost nothing. The thing that's really expensive is time running on the computer. So you can, you know, the humans have to pander to the computer. They have to do all these things to make sure the computer is as happy as possible, and then they can run on that computer. But in today's world, of course, it's the exact opposite. The computers are, you know, it's easy and cheap to do things on a computer. What's expensive is the human time and the human effort of thinking about things, and that's the limiting factor. So it's a completely different situation from the way it was in the early days of programming. But a lot of what people think about in terms of programming, computer science, and so on, is based on that sort of tradition of make it easy for the computer, so to speak, rather than formulate things in a way that corresponds to the way people think about things. And of course, the things that people think about are not the same things that computers intrinsically know about. People might talk about colors, or they might talk about things about types of animals or something. And those are things which, yes, you can represent those computationally, but that's not intrinsically what computers do. You have to have this layer, large layer of computational language to actually communicate with computers about things like that we humans care about. So it's one of the things that is a sort of a question about programming computers is the sort of the concepts that are involved in learning to sort of think about things computationally. So, for example, and then there are, so for example, one very simple concept is you can have a whole list of numbers and it's just one thing. And you can, let's say you add 1 to it, well, it just adds 1 to all the numbers in that thing. Or you can kind of treat that whole thing as a single thing. You're not having to say, oh, it's got all these elements. Let me you know, adjust each element separately. That's a very elementary kind of idea, but it's an idea that still feels advanced when you think about computing in terms of the way that computers are intrinsically built. Now, another question. So for example, let's say you have that thing. It's a big, long list of numbers. You want to do something to it, add 1 to it, whatever. One thing you can do is have some sort of procedure for doing it, where you say, first add 1 to the first number, then the next number, then the next number, then the next number. The other thing you can do is say, I've just got this function, and this function adds 1 to things. Now let's apply that function to this whole list of numbers, and oh, it will do that on all these separate numbers. And so there's kind of a distinction that's sometimes drawn. I don't think it's really that fantastic a distinction between what one might call procedural programming and what's sometimes called functional programming. And the book that the person who was asking this mentioned is a book very much oriented towards functional programming. The concept is, do you program by sort of saying, do this first, do this next, do you break it down into these sort of individual little pieces, or do you say, I'm just going to take this whole function and I'm going to do, the function f, I apply that to my what I've got, then I apply the function g to that, and I just build up this series of functions, as opposed to saying sort of inside, how do I do the micro work to put things together. Now, I have to say that in my efforts in sort of building computational language, I found that it's sort of a mistake, because sometimes there are times when these different styles of programming are the natural way one thinks about things. So to say, no, it's got to be this way and it can't be any other way is sort of a mistake, because we humans think in a variety of different ways, and you kind of have to be able to capture those. And the real challenge in terms of language design is to have all those pieces fit together. There's actually another kind of sort of different, perhaps, way to think about programming that I found extremely powerful, which is what one might call symbolic or pattern-based programming. And here's how that works. So you say, you build up some structure. It might be this thing. What is that structure? It's a symbolic expression. So often when you talk about computer languages and things, you say the thing called X. You just sort of type X into your computer is going to say, what is X? I don't know what X is. X doesn't make any sense to me. X is, it has to be a number. It has to be a string. It has to be something else. It has to be something that is intrinsically known to the computer. But actually it doesn't. It's perfectly possible to just say, X is just X. It's just a symbolic thing X. And as soon as you have this idea that it can just be a symbolic thing X, that symbolic thing could be something that represents a city, or something that represents an image, or something that represents all kinds of different things. But that is then just a symbolic thing. It isn't something where you say, and I must know how it is implemented down in the hardware of the computer, so to speak. It's just a symbolic thing. Now you can start building up a whole structure with that. You can say, oh, I'm going to have something that represents, I don't know, a collection of, let's say just a collection of cities. Just be some list of cities. It's just a symbolic thing that is a list of cities. And or let's say another kind of symbolic thing might be an algebraic formula, something, x squared minus 2x divided by y, or something like that. That thing, we're not saying what the value of x is, the value of y. That's just a symbolic thing that sits there as the kind of thing you might do algebra on. But it's a thing that isn't something where the sort of it's translated down into something that the computer immediately was set up to think about, like numbers and so on. So you can represent these things just in a sort of symbolic way. And then the question is, what do you do with these symbolic objects? Well, the answer is that I kind of came up with like 40 years ago now as kind of a way to think about these things, is more than 40 years now, 43 years ago. That you just say, what is the structure of this thing? It is some symbolic expression. And that symbolic expression might be, I don't know, it might say disk of coordinate value, comma, radius, and so on. That's kind of a symbolic expression. And then there's one operation that you want to do, which is you want to make transformations for symbolic expressions that match certain patterns. So for example, let's say that we have a list, 3 things. And let's say it could be a literal list of 3 things, 1, 2, 3. Or it could be a list where we don't know what the second element is. It's 1 at the beginning, 3 at the end, and there's anything in the middle. So like in Wolfram language, you would just represent that list as list 1, comma, underscore, standing for, we call that blank, comma, 3. And so that thing, 1 underscore 1 blank 3, that is a pattern that represents a list. Starts with 1, can have anything in the middle position, then 3. So now we can say, okay, let's say we've got a whole bunch of lists. We could say, let's transform that whole collection of lists with the rule that says anything that looks like 1 blank 1 anything 3 gets transformed to something else. So that's a transformation rule for a pattern. And we can generalize that a lot. So for example, you would often think about, let's define a function in a computer language similar to the way it's done in mathematics. You say some function f of x let's say, is x squared. So that says whenever you, so one way to interpret that is whenever you see f written down, open bracket, let's say, something, let's say the number 7 or something like that, f of 7, whenever you see f of 7, if you've said that f of x is x squared, what you mean is that f of anything, name it x, is actually supposed to be transformed to x squared. So like in Wolfram language, you would write f of x blank equals x squared, for example. And so what does that mean? It means whenever you see a pattern that has the form f of blank anything, that blank is named x, transform it to x squared. So it's giving this transformation rule for a symbolic expression. And turns out that's a very powerful way to do things because it allows you to deal with data of any structure, things that represent all kinds of different, I don't know, graphs or audio or whatever else. You can represent any of those kinds of things as a symbolic expression. And then these transformations that you make on symbolic expressions can be incredibly general. It doesn't matter whether it's a piece of graphics, whether it's some representation of some running program, any of these other kinds of things. You use the exact same apparatus to be able to deal with it. And that's the sort of the value of this kind of idea of symbolic programming. And so pattern matching, you just say, whenever you see an expression that looks like this, transform it into one that looks like that. That's a really powerful way to set things up. And sometimes it's convenient, and that's sort of this kind of symbolic pattern-based programming. That's sort of a core thing in our Wolfram language system. Functional programming, it's more like you define some kind of function, and whatever you feed it, it's going to eat it. So one of the things when I said f of x blank, colon equals whatever, let's say we wrote f of x blank, comma x blank. That is equal to whatever it's equal to. What does that mean? That means whenever you see f of something and then a second copy of the same thing, then transform it. But if you see f of 1, 2, for example, 1 and 2 are not the same, they don't match the same pattern, it doesn't transform it. It doesn't define a transformation for that. So what happens with this kind of pattern-based approach to describing computation and so on is you say, whenever you see something that looks like this, and it can be a very complicated this, and it can have some sort of holes where you're filling in specific values and so on, transform it this way. It's a very powerful way to do things. In the more traditional kind of functional programming way to do things, you say, I have a function, and whatever it's fed, it'll always eat it and do some particular thing to it. And there are ways to kind of make that a little bit more nuanced by, various kinds of types of objects that you feed it and things like this. You can identify sort of different things that you feed to a function as being of different types. Like one might be an integer, one might be a string. That's a very simple way. It's a very kind of impoverished way to think about this. The right way to think about it, I think, is that you're saying you've got this symbolic expression and it can have an arbitrary form. And whenever it has a form that matches this pattern, then you do this transformation. And when it doesn't, you don't do this transformation. When you're just dealing with types, you say, whenever it happens to be an integer, then do this. But actually, you might say, well, I really just want it to be transformed if it's an even integer. Well, that's a hard thing to represent. You basically have to say, well, do the transformation anyway. And if you find out, or evaluate the function anyway, and if you find out it isn't an even integer, then do something different. It's much better, more convenient, and the generalizations of that are much richer when you just say, we've got this arbitrary symbolic expression that we can specify as being the pattern that describes what to do. So anyway, so there are these different kind of styles of programming. Now, one thing to say is when you see, for example, pattern-based programming, it's very kind of obvious what's going on in most cases. Like everything, there will be sort of, it's very much, you hardly have to explain anything. Functional programming, there are some things to explain. There's some things that are a bit, they're ideas. Once you have the idea, you can really run with it. I mean, I think it's kind of a little bit like learning something like calculus, where there are a certain set of ideas, and once you have, once you sort of have that idea, you can you can really run with the idea. So I'll just describe one idea that's sort of an idea of functional programming. It's implemented in I would say, a particularly clean way in Wolfram language. It's the following thing. So I mentioned you have, well, let's see, you can have, you have everything in Wolfram language is a symbolic expression. So for example, 1 + 2 is a symbolic expression. What is it? It's the plus function basically applied to 1 and 2. Now so plus is a built-in function. There are like 7,000 of those in Wolfram language. It's sort of comparable to the number of words in a typical human language. But that's a built-in thing. But now you say, okay, I'm going to, another function might be times, another function might be, random integer. It might be, there are all kinds of different functions that you can use there, and you just apply them to their arguments, let's say 1 and 2. Okay, now a question is, what happens if you just want to sort of create a function on the fly that you're then going to throw away? Is there something you can put in the position of that plus that is what one might call a pure function, a thing that just represents a function? Like, let's say it represents the function that adds 13 to something. How can you make a thing that is kind of like just a symbolic expression that represents that function, that you can put into the place where you did have just the name plus, and have that thing be something that adds 13 to things? Well, in Wolfram language, that would be something like, you could write it as function, x, x plus 13. That thing is a symbolic expression. Just say that thing, let's say open brackets 1, 2, that whole thing applied to arguments 1 and 2. And so this idea of this sort of big head for the function, instead of just being plus or f or something like that, it's a great big symbolic expression that represents a function to evaluate. That idea, sort of a higher order function idea, where you have the notion that instead of it being a fixed function like plus or times or something like that, it's this thing you can construct that you can carry around as a symbolic expression. You could say, v equals that thing that represents the function, and then you just put that in somewhere and it will evaluate itself to be that function. So this idea of pure functions, anonymous functions, these are also essentially lambda functions in the sort of historical development of mathematical logic. That's what things like this were called. That idea is a very powerful idea. It's a very convenient idea for actually writing programs. When people first see that idea, they're like, that's a bizarre, abstract idea. When would that ever be useful? And I've noticed that people have to have a certain amount of experience in just writing programs, particularly computational language programs, symbolic computational language programs. They have to have a little experience, at least using symbolic language to represent things. And then after they've had that experience, you finally show them this idea of pure functions, and they, having had that experience, they'll get that idea, and then they'll be writing pure functions fluently from that point on. But it's an idea, and it takes a bit of kind of a little bit of getting used to it. If you're first presented with it, of, guess what? You can do this thing where you abstract away this notion of a function into this symbolic object that is then applied to things. It's very bizarre and abstract and hard to understand. I should just mention okay, all kinds of interesting questions here, and I fortunately have to go very soon here, but I should just mention a sort of a bit of an irony of sorts. This idea of making transformations for symbolic expressions, this idea that's sort of been the backbone of the things I've done in computational language the last 40 or more years, turns out that idea is also, though I didn't realize it until after I'd sort of separately invented these ideas, is actually the same idea as we're using to understand how fundamental physics works. In fundamental physics, instead of a representation of sort of symbolic expressions where they're pluses and timeses and things we know what they mean, in fundamental physics, what we have is kind of well, it's a hypergraph structure, but it's basically something like a symbolic expression. And we're just saying, whenever you see a little piece of symbolic expression that looks like this, transform it into that. But instead of it being a symbolic expression where the pieces of it are things we intrinsically understand, pluses and timeses and things like that, the pieces of it are atoms of space. They're things that are absolutely microscopic pieces of the way our universe is put together. There might be, you know, a trillion, whatever of these in our universe. And these atoms of space that we might be calling things like plus and times, when we use them in when we use them as symbolic expressions in our computational language, the precise analog of that is the things that are happening in the structure of physics. But in the case of physics, they don't have names. We don't have, there's nothing special, you know, the particular atoms of space that are being created, destroyed all around us all the time, they don't have names. There are some sort of, perhaps somewhat bizarrely, at the center of black holes, there are places where there's sort of a single atom of space that is kind of stuck there and not updating with time. It's a place where time has stopped. And I suppose one could give those names because they're sort of persistent things in some sense. But most of the time, it's kind of the unnamed symbolic expression thing. But it's sort of an irony, at least in my life, that, you know, having used these things for technology and for developing computational language, turns out that the exact same idea is the foundational idea for thinking about physics. Although, as I say, strangely, and it's just sort of the way that these things evolve, the way I thought about these things was in terms of the physics thing is about graphs and networks and this and that and the other. I didn't think of it as symbolic expressions. It was only after we developed a lot of stuff in that direction that I realized, my gosh, it's the same idea as in the case of computational language. Now, I have to say, a thing I've been working on recently has to do with the foundations of mathematics. And that's a place where these two ideas, the sort of physics idea and the computational language idea, they kind of merge in an interesting way. And we kind of get to understand sort of what's underneath mathematics, just as we're trying to understand sort of what's underneath physics. And sort of the spoiler alert is, it turns out it's the same thing underneath mathematics as underneath physics. And in some sense, what we are, when we are perceiving the physical universe, we're perceiving it in a certain way, in the way that we sort of parse out what counts as moving around in space, what counts as progressing through time, and so on. That's something that we take out of kind of all the stuff that's happening intrinsically in the universe. And similarly, when we do mathematics, turns out there's the same intrinsic stuff happening, but the things we take out of it as sort of mathematical observers are different from the things that we take out of it as observers of the physical universe. So anyway, that happens to be the thing that I'm interested in right now. All right, looks like we have some lot of interesting topics and questions, but I think they will have to wait for next week. But so, well, thanks very much for joining us, and look forward to talking to you again next week.